Alright, so we observed an instability in the last video where once the R was greater than equal to 0.5 and greater than 0.5, an oscillation occurred. There's an instability in the overall plot. So we are going to perform a von Neumann analysis in order to show why that instability occurs. So let's begin with rewriting out this quick simplification. Oh, over time is equal to alpha this is x squared. Cool. In reality, tk is equal to e to the I k x. I is an imaginary number, k is your diffusivity constant, x is your position. Multiplied by alpha k squared t as in time. Awesome. So now we're going to write a couple, as you can see, we can now write a couple equations that relates to these parts here, and these are actually, after I write them, these are actually Euler equations. So e to the I k x is equal to cosine k x plus I sine. We're gonna do, I like that. I sine k x and e to the negative alpha k squared t is equal to cosine k x minus I sine k x. So the thing about tk is we can actually think of it as a summation. So continuing on, this is our like our actual temperature profile, which we're signifying as tk. You can think of this as a summation. So it's equal to the sum as k from k infinity to k from k negative infinity to k infinity. And that is going to be of ck multiplied by e I k x e to the negative alpha k squared t. So now that we're going to keep these up here because they will be useful to us later. We are going to bring back our our finite differencing equation we derived earlier. So they're going to do t j plus 1, because we're looking for the next step, is equal to t j to the n plus r. So we're taking that alpha change in t over change in x squared, and we're just going to call that r. Multiplied by t to the j plus 1 n minus 2t plus t j minus 1 n 1. So now we can take our summation and actually solve for t j plus 1 and t j minus 1. So tj plus 1 is going to be e to the I change ik change in x and all multiplied by t j to the And then tj minus 1 is going to be e to the negative k, change in x, multiplied by t, j, n. Alright, so we can take these and plug them back into here. So we're going to do t, j plus 1. We're going to keep this as such, equal to t, j, n plus r. That was our substituted right there. So now we know that tj plus 1 is now equal to e I k, change in x, t, j to the n minus 2 t, j to the n plus, because we're trying to simplify this down, so now we're also plugging in the t, now we're plugging this into the tj minus 1, that's a minus, e minus k, change in x, t, j, n. Awesome. Alright, so now we actually have a fun situation where we can simplify, where we can divide by tj to the n on this whole side, which is awesome. So now we're just going to pull out that tjn. We're going to keep this as tj plus 1 on this side, but now we're going to have tj to the n. We're going to have 1 plus r e I imaginary number, thermal diffusivity, change in position, minus 2 plus E negative K X T. Oh no, that got taken out. Change in X. There. So we have that simplified down now. And now we can even simplify it more because we have our Euler equations. So you can see that this here is we got the same going on with this, and the same here, so that we can now simplify it down. We're going to bring this up over here. So we're going to have t plus 1n is equal to t j n is 1 plus r. Yeah, because we're adding them together. So the thing is, we're adding this together, so the cosines are going to add. So yeah, it's going to be 2 cosine kx. And the signs are going to cancel out. And then we're going to subtract 2 from all this. Yep. And then that simplifies down to there. And now we see something that can happen. So now we can we have limits. So we know that at a certain point, we're trying to find that whole like 1/2 situation. So we can actually pull this out. So we're going to analyze the stability. So for stability, we're going to analyze this section here. So we know that the function of cosine oscillates between -1 and 1. Is 1 plus r, 2 cosine change in x minus 2 less than 1. So we're going to simplify this all down and solve for that value of r. So let's just do the math. Awesome. We're shifting. I'm going to pull this out over here so we have that -1 is less than the r pretty much multiplied by -2. So then we solve for this, and we see that r is less than 1/2. And you wonder why that is. And that is because for sine and cosine of their amplitudes, once you get over 1/2, it is a multiplicative factor. So it will cause it to make those oscillations overall, and it causes this overall instability. So in order to use this equation, you have to make sure that your r is less than 1/2. So now we see that r has to be less than 1/2, and in the case that we saw in the problem before, r was greater than or equal to 1/2. So in the case that r is greater than or equal to 1/2, this would cause stability issues due to the multiplicative factor of sine and cosine, along with the amplitudes of sine and cosine that would cause this to destabilize, and therefore, as you could see in the previous, we had oscillations throughout that answer. So we have to make sure with this stability analysis, r has to be less than 1/2. That is the conclusion of the stability analysis in order for it to remain stable.